This next section is about reaction rates using balanced equations. So here is a reaction rate. We're going to be using this general equation right here. You have little a plus little b, big B reacts to make little c, big C plus little d, big D. So what in the world, why do we have the same letters but just in uppercase and lowercase? These lowercase letters are going to equal our moles. And those are just the numbers that are in front. This right here is simply going to be our compounds. So we have seen this before, we have moles and compounds. This is just a general reaction. Okay, we can write our reaction rates the same way we were doing before, but instead our reactants are going to be a negative, so they all can be equal to each other. This is because reactants are going to slowly disappear and products will slowly be made. So you're going to take the delta A, or the change in the concentration of A, all over the moles of A times the change in time. And that will be a negative. The same thing is said for B, negative as well, but C and D are a little bit different in the fact they're going to be positive because they're going to be made. So reactants are negative because they are being used up. Products are positive because they're going to be made. And these all equal the same rate. So let's go ahead and look at this reaction. We have this reaction. We have N2 plus 3H2 reacts to make 2NH3. Let's go ahead and tell you more information on this before we get started. So as the reaction progresses, the concentration of H2 goes down. Here's our chart. We're going to have concentration on this side, time on the bottom, and then you can see the concentration H2 slowly goes down. And it is a curved line, not a linear line. Here is another slide. You have to look really closely, but there is N2. Our line slowly goes down for N2. Not as steeply as it does for H2. It actually goes down 1/3 as fast. So the reaction progresses for the concentration of N2 goes down 1/3 as fast. And if you remember our reaction, there was 3 H pluses for every one of these. So that's why. Let's just go back. I'll show you that real quickly. So right here, we only have 1 of these and 3 of these. So therefore, this one's going to go 3 times faster, get used up 3 times faster than that other one, than N2. All right, then here's our last part. As the reaction progresses, NH3 is going to go up because these two, our H2, our hydrogen, and our nitrogen are going to get used up. So ammonia is then going to increase, so it's going to be what's going to be made. So our total chart looks something like this. You have H2 going down, N2 going down, not as fast, and then NH3 increasing. So let's talk more about this. So calculating rates. Calculating rates are we usually talk about average rate. That's how we've done it so far. And that's by taking over long interval. That's where we're doing the change in the concentration over the change in time. We can also do something called instantaneous rates. These are determined by finding the slope of a line tangent to the curve at any given point because rate can change over time. So this does change. So rate depends completely on the concentration. So if we go back to look at our concentration of hydrogen, you'll see that it's a very sloped line here at the beginning, and it gets still pretty steep, and then it slowly starts to get more flat. So we usually take just the change in the concentration all over the change in time. So the concentration over time, just 2 points. We pick 2 points, and we take the difference of them, and that's how we find our slope, rise over run. That's all we're doing here. But an instantaneous slope is where you take a curve and you make a line tangent to that. So it goes through that 1 point, and you make a slope of that. Then you would find the slope of this line. That will be an instantaneous method of doing so. All right, let's go back to our reaction. So again, defining rate. We can define rate in terms of disappearance of the reaction, or the reactants, or the appearance of the product. That's why we have positive and negative. So back to our example here, we have N2 plus 3H2 reacts to make 2NH3, or nitrogen plus 3 hydrogens makes 2 ammoniums. If we look here, this number up here is really just a 1 in front, so in front of here, we really have a 1 as well. So we're having a negative change in the concentration of N2 all over T2. Then we look over here, we have the negative change in the concentration of hydrogen all over 3 times our change in time. And again, we put a 3 there because we have a 3 for our number of moles. Then we look at our last one, it's now positive because it's a product, and we're taking the change in the concentration of NH3 all over 2, the change in time. So those are very important. Let's also go ahead and talk about our rate laws. So all reactions are reversible. This is very important. Make sure you know this. They are reversible. As products are going to accumulate, they are going to begin to turn around and turn into reactants. So as you make products, they're going to turn around and go back to reactants. So at the very beginning of the reaction, you completely depend on the reactants only because there are no products. So you can only depend on the reactants. We want to measure the reactants as soon as they are mixed. This is called the initial rate method. The initial rate method only depends on the reactants because that is the only thing that is present. So here let's talk about this initial rate. So 2 key points about the initial rate law. The concentration of the products do not appear in the rate law because it is the initial rate, because they don't matter. They aren't there yet. They don't exist. And the order must be determined experimentally. So you have to determine an order of a reaction. You cannot just look at the equation to determine the order. It has to be determined experimentally, or you have to be given the experimental data to prove it. So let's go back and look at this. So here we have a reaction. Okay, we have 2 nitrogen dioxides react to make 2 nitrogen monoxides and oxygen. So you will find that the rate will only depend on the concentration of the reactants. Again, reactants are on the left, so that's what we're going to look at. So rate is going to equal to K, and the concentration of our reactant NO2. And then it's going to be raised to some power. This is what we call an order. Again, we cannot determine the order unless it's done experimentally or we're given that data. We'll talk about that. So this is a rate law expression. K is what we call the rate constant. It's a constant for this reaction. So if you don't know what the constant is for this reaction, you can determine that experimentally. And then N is the order of the reactant, and it's usually a positive integer, like 1, 2, or 3. Those are the most common. So let's look at another reaction. Now we're taking the one we had before, nitrogen and 3 hydrogens to make 2 ammoniums. So here we're going to say the rate is equal to K, some constant, our rate constant, times the concentration of N of nitrogen raised to the M power. Again, this is just an exponent. And we don't know what it is. We don't know the order of N2. And then we're taking it times the concentration of H2 raised to the N power. We have 2 of them now because we have 2 reactants. So we have to have 2 here as well. The overall order of the reaction is all of the powers added together. So in this case, the order of the reaction would be M plus N. So if M equaled 1 and N equaled 1, the order of the reaction would be 2. Another thing that could be true is that if it was 2 plus 1, it would then be 3. So it's just if M and N equal different things, that would be how you determine the order, if you knew what M and N were equal to. Usually this has to be done experimentally. All right, last slide. Let's go ahead and talk about the other types of rate laws. There's a differential rate law that describes how rates depend on concentrations. Depends on concentration, so it's all dependent on concentration. The integrated rate law talks about how concentration depends on time. So for each type of differential rate law, there is an integrated rate law and vice versa. So there's an equation for each one of these. We're not going to go more into them than this. So rate laws can help us to better understand reaction mechanisms. They're very important in determining how things work. All right, make sure you're doing your quizzes.